Thank you. Thank you very much for the nice introduction, and also thank you to you and all other organizers for the invitation and the possibility to present my work here. What I'm going to present is joint work together with Alex Bespalov from the University of Birmingham and Dirk Praetorius from TU Wien. I'm a bit disturbed by all the arrows on the screen. Oh, it's also mine. Okay. Well, great. Yes, so as the chairman said, I will continue a discussion on adaptive stochastic multi-level, so adaptive multi-level stochastic Galerkin finite element methods, but yeah, the focus will be different. In particular, as the title suggests, my main aim will be to present some results on convergence and rate optimality of the algorithm. But before I start, let me maybe to give a brief sketch of what I'm going to present. Let's start from a very general setting, so just a variational problem encoded in this variational formulation here. And we want to consider a standard Galerkin method for that. So we all know how it works. We just consider a finite dimensional subspace of the space here, and we just consider the restricted problem. So the problem restricted to the finite dimensional subspace here. We will need some, our upcoming setting will need some properties here. So we will assume that there is an initial approximation space here V0, and we assume that all possible discretization space that we will consider in our methods essentially will contain that. And we will also assume that there is a very prescribed procedure to construct spaces that are used in our algorithm, and this is somehow, in some sense, we define a fixed set of possible admissible approximation spaces here. Okay, and now once we have that, we would like to employ an adaptive algorithm to solve the problem. So consisting of the standard 4 modules: solve, estimate, mark, refine. And so at each iteration, in solve we compute the current approximation. In estimate, we compute the associated error indicators, eta here. We should somehow give information about the error here, consider with respect to the energy norm. And then, we mark something in order to improve the approximation, which will then improve in the final module, refine. Okay, so the questions I will discuss in this talk are the following. So does such an adaptive algorithm converge, in the sense that either the error estimate eta or the energy error or both, so they are usually related to each other, so information about one will give information about the other guy. So does this converge as L goes to infinity? And the second question will be about the rate. So do we have a rate, and is this rate optimal with respect to the number of degrees of freedom of the approximation space? So something like that, old with S as large as possible. And the third question will be, so essentially the first two in the setting of so-called goal-oriented adaptivity. So the first two, say, I will call them standard adaptivity, when the aim is to approximate in the best possible way the solution itself with respect to the energy norm in our case. And in so-called goal-oriented adaptivity, the target is a quantity of interest depending on the solution. So essentially, yesterday we have seen essentially answers to these questions in different settings. And I hope that nobody complains if I say that for the deterministic setting, where by deterministic I mean parameter free, so not in the context of parametric PDEs, the problem is in good shape, so more or less understood for a large class of problems for a number of numerical methods and adaptive algorithms. Of course, as usually mathematics, there is always work to do, but an answer is there, essentially. Much less is known, on the other hand, in the context of parametric PDEs, in which the differential operators maybe depend on an infinite set of parameters, okay? But still there are answers, and here are some of the works addressing that, and in particular, so as far as I got from the abstract, we will see some other answers this afternoon in the talk by Markus Bachmann. Okay, so this is the focus of my talk, and I will do that for the stochastic Galerkin finite element method, but and for a particular class of so for a particular choice of the adaptive algorithm, the estimator, and so on. But essentially, by doing this, a byproduct of our work will be that now we have a kind of framework which will allow us to consider other choices somehow to tackle these questions. So this is the outline of the talk. I will essentially to present my notation, because most of the things have already been said also in the previous talk. So the discretization will be, and so there will be some differences, but other aspects will be in common. So we'll repeat them in particular because the notation will be different. So it's good to repeat things. And then I will present the main results in the context of so-called standard adaptivity, and then say a few words for this, in the interest of time, for the case of goal-oriented adaptivity. So let's start with the model problem. It's the stationary diffusion problem here, where the diffusion coefficient and possibly also the right-hand side depend on an infinite set of parameters. Here we consider the infinite hypercube, which we call the parametric domain, and this is the physical domain in 2 or 3D. For the diffusion coefficient, we do the following assumption. So we consider an affine dependence of the diffusion coefficient on the parameters, and somehow these assumptions guarantee that we have a so-called uniform ellipticity assumption. So the problem is well posed, essentially. Okay, so the variational formulation that I presented in the introduction associated to this problem will be well posed. Okay, and this is the variational setting for that. So I will call by X somehow the Sobolev space H10 in the physical domain. P will be L2 of pi, so X will be considered with respect to the standard Lebesgue measure. And on the other end, I am assuming a probability distribution, okay, of this form here associated with the parameters, okay? Then the underlying space V is just, yeah, L2 of pi with value in X, okay? And it is isomorphic to the Tentus product of X and P. And okay, I just consider, as in the previous talk, so the bilinear form B associated with the problem, and are reduced by linear form B naught, which is in our case the one associated with the parameter-free part. Okay, and then I just write down again the problem that we saw in the first slide. Okay, for this special situation. Now I would like to briefly introduce the stochastic Galerkin discretization finite element method that we use. And the starting point is what has been discussed also before. Okay, we consider a so-called generalized polynomial cause expansion here. So the index set here is the one of finitely supported multi-indices. These P guys here that before had a different name are the tensor product orthogonal polynomials, and the coefficients here are unique in H10. Okay, and so this expansion holds true for any function in my space V. So in particular for the solution, okay, that we are looking for. And the starting point, this is the starting point to construct a discretization. First, we do a semi-discretization in parameter. Essentially, this is obtained by truncating the sum here. Okay, so we just consider a finite index set and then just truncate the sum here. Okay, but the coefficient in this very moment are still in H1, 0. To obtain a fully discrete numerical scheme, somehow you want to approximate then this coefficient, and our choice will be a standard finite element method, okay? And essentially, we will go the multi-level way. So we have discussed it, the difference between single level and multi-level has been discussed in the previous talk. Somehow the main idea is that you want to improve the quality of your approximation space, but retaining the dimension of it as small as possible, because in the context of infinite many parameters and so on, you have to face the so-called curse of dimensionality. So you have to be careful by increasing the dimension of our approximation space, and this can be done by, so this, a way to achieve this is this way, okay? So for each coefficient, so for each multi-index in my current index set, I consider a mesh, so the way they can be all the same as in the second level method, but in general they will be different. I consider the space of piecewise linear and globally continuous finite elements associated with it, and I will approximate my coefficient there, okay? The resulting expression of the space V is written here down, and its dimension is given as the sum of all of the dimensions of all finite element space, and somehow you get a feeling why somehow here this allows to be more careful when reaching the dimension of the space. Here we have a sum, and in the single level setting we have a product, okay? So it's much easier to reach large numbers in the single level setting, okay? This is the discretization, and in view of the upcoming analysis, I would like to introduce the notion of a multi-level structure here, which is somehow the object, so the thing which stays behind the approximation space. Like in standard finite element methods, where your approximation space is, there is an underlying mesh somehow behind it. Here there is such an object which is made of the index set and the collection of meshes here. And for that guy here, I will introduce a notion of cardinality here, which is defined here, okay? And the important thing here is that this is essentially up to multiplicative constants. This behaves like the dimension of the approximation space, okay? We will need this information later to define approximation classes and so on, okay? Okay, so once we have a space, then the question is how to build the next one, okay? So how to improve the quality of our approximation. And essentially here with slightly different choices, but the process is the same as we saw in the previous talk somehow. So we start from an initial multi-level structure, which will be as easy as possible. So the index set will contain only the one index, so it will be a singleton containing the 0 multi-index here, and we will associate a generally coarse initial mesh here, okay? And there are essentially two ways to improve the quality of your approximation, right? So you can do either mesh refinement, in the sense that, so for the mesh that you have, you mark some elements and then you build the coarsest mesh in which the coarsest refinement in which those are marked, and this is encoded by this guy here, refine. And we will call, say, T at the mesh which is obtained by performing a uniform refinement, okay? So in this case, by doing something like that. And in the parametric, to enrich the parametric index set, it's we do as it was done in the previous talk, essentially, namely, we consider some candidates in a so-called detail index set. Sometimes this is called boundary, sometimes this is called margin. I'm not giving here the precise definition that was given in the previous talk. Somehow these are kind of neighbors of those that are currently in the index set. And we will mark some of them and just add them to the discretization, okay? And again, I will consider a net guy, which is the equivalent of uniform enrichment, in which you add all candidates that you have. Somehow we have both ways to improve the quality, and I would like to introduce now a concept to formalize this, that we can do both somehow. So given a multi-level structure, so an index set and a collection of meshes, given some marked guys, so some marked indices and some marked elements for each mesh, we consider a routine refine here in capital letters, which does the following. So it augments the index set. For each mesh that was already in the index set, it does refinement. So given the elements that have been marked, okay? And for those that are added, they also need a mesh. In our case, we will consider the initial mesh, okay? And this procedure leads to so the resulting spaces are nested, okay? So if you start from a multi-level structure, you consider the related approximation space, you do multi-level refinement, the resulting space, in this way, the resulting space will be a super space of it, okay? It will contain the original one. And I will define this guy here, refine P naught, which is the set of all admissible multi-level structure allowed by our method by considering a fixed refinement rule for the mesh and by considering this approach for adding the index set, okay? And this somehow reflects the set of admissible approximation spaces that I was mentioning in the very beginning. And again, there is a net guy, which is the equivalent of uniform refinement. So it is a uniform multi-level refinement, which is the one that is obtained by doing everything. So you refine uniformly all meshes and you add all possible indices, okay? This is just a formalist. And before going to the posterior error estimation, I would like to introduce an auxiliary Galerkin approximation, so which will never be computed in practice. It is the one associated with the uniform refinement, so multi-level refinement of the current space, okay? This is in view of the fact that our error estimators will be of hierarchical type, okay? You know that, okay, there is orthogonality here, you get the error reduction here, and in general, this will lead to a not towards approximation. So this is very, very standard, okay? Now let's go to the estimator, and as it is customary in this setting, our estimator will have two components, one associated heuristically with the error in the spatial, to the spatial error in the physical space, and one associated with the error in the parametric, of the parametric component of the solution. And for the spatial case, we use a so-called two-level error estimator here, which was essentially introduced in the context of boundary elements. At least this is where it can be found more than 20 years ago. And essentially, this consists of dual norms of the residual tested, so computed for somehow the Nuet functions that you would get by doing, say, uniform refinement, okay? So you get some of the set of all interior midpoints in 2D, essentially. So this is the picture. You get a net function that this is the one that you could add in the formalism of the previous talk in order to improve your approximation. And this is what we get. And then, yeah, to obtain the element guy, you just sum the three midpoints, at most three midpoints of it. And if you sum over all indices in the current space, in the current approximation space, you get then an estimate of the X error here, okay? So we discussed this first for the single level setting and recently extended it to the multi-level setting. For the, as a parametric error indicator, we consider a hierarchical indicator, which is basically the same guy of the previous talk. One difference here is that here we really test with the coarse mesh, okay? Which makes this problem very cheap to compute. Okay, we have both components, so the overall, the total error estimate will be considered by the will be obtained by summing these two components here. And this is the theorem concern about the posteriori error estimation. Okay, so we can show that somehow the error estimate, the total error estimator here is equivalent to the error reduction here that you would get by performing uniform multi-level refinement. And this has easy, straightforward consequences related to the orthogonality that was shown before. So we get efficiency for free always for the error estimator under a so-called saturation assumption. By doing uniform refinement, we will not only not get worse, but we obtain a strict improvement of the solution under this assumption, and actually this is equivalent to that. Our estimator, hierarchical estimator, will be reliable. Okay? Fine. Now we have an error estimator. We can consider an adaptive algorithm where we use that. Okay, and as I said in the very beginning, we will go for the well-known approach, solve, estimate, mark, refine, where starting from the initial multi-level structure, which determines the first approximation space, we solve, so we compute the solution of our problem. Then we estimate, so we compute all the spatial and parametric error indicators. And when we mark, and this is a remarkable difference with respect to the previous approach. So in the previous approach, we have seen that usually you compute both spatial and parametric error indicators. You then obtain somehow two estimates, the one morally referring to the error in parametric space and the one in spatial space, and then depending, for instance, in the potential error reduction by doing either mesh refinement or parametric enricher, or by comparing these two, essentially, you do either or. What we do here is different, so we just put all error indicators, so those all spatial ones associated with all meshes and all parametric ones, we put them in the same pot, and we do Dörfler marking there, okay? Based on some parameter theta here, fixed here. And once, so somehow it turned out that we get some marked guys here, which could be both, so simultaneously elements or indices. And then we do the multi-level refinement according to the outcome of marking. In general, is it possible that we get both elements and both indices to add? And actually, not only this is possible, this is what will happen in practice in our simulation. Okay, and as a side remark, also a practical realization, so we are interested in asymptotics, so convergence, but a practical realization of the algorithm will stop after test 2 if the error estimate is smaller than some certain tolerance. Okay, so before I enter the, say, the convergence stuff, maybe a quick break with a numerical experiment. So I consider this problem here also considering the previous talk somehow, which is a kind of, at least for us, a benchmark problem, because we always test our algorithms with that. Okay, so but on a L-shaped domain, this is maybe a difference with respect to the previous calculation. And yeah, let me maybe mention that all the computation that I will present, that we did, and we had in particular those that I will present in this talk, have been computed with stochastic T-IFIS, which is maybe another son of IFIS, where the T stands for triangular. Okay, the previous talk was about quads. We will consider triangular meshes in view of so for our algorithm. So this is open source, can be downloaded from the following web page, so basically the web page of Alex, and yeah, it can do many things. So goal-oriented, as we will see later, single-level, multi-level approximation. So if you're interested, for instance, in reproducing our numerical experiments, you can find the code there. But let me present first some pictures. Okay, here I would like to showcase somehow what the multi-level does, the multi-level approach does. Here we see three different coefficients of our approximation, and you see that, so basically depending on the shape of the solution, and maybe in some sense on the importance of the solution, somehow the number of elements and so the parts of the domain which are resolved can be different. Okay, the corner will be refined by all machines because this is intrinsic, a geometric singularity intrinsic of the problem, okay? But for the rest, there is some flexibility, and this is the way how we achieve somehow a good accuracy by comparably a smaller number of degrees of freedom. And then here are some rates. So you see that by doing, say, so uniform, of course, cannot work. Okay, so when we do we add really everything. So you see, it seems that there is still some convergence, but the rate is really poor. Then the red line is adaptive, but with single level, so the same mesh for all indices, and with this separate marking approach, okay, in which you do either mesh refinement or polynomial enrichment, and you see that the rate improves. Then you see a further improvement if you go multi-level. Okay, you see, again, if we keep for the moment the separate marking approach that I briefly discussed before, and go multi-level, the rate improves. But if we do somehow, if we apply the algorithm that I presented before, so combine marking and multi-level, we get the best rate. So among these 4 cases, and in particular, the rate will be 1/2. And this is the optimal rate for associated with first-order final elements in the case of the parameter-free problem. Okay, so this is remarkable. Somehow Dörfler marking, which will play a role for us for the analysis, seems also to be a good choice in terms of performance here of the algorithm. But now we would like to enter convergence. And the first question that I mentioned in the beginning is plane convergence. Okay, so does the algorithm, does the error estimate in this case go to 0 as L goes to infinity? And the answer is yes. Okay, for any choice of the marking parameter theta, we get convergence. And the proof basically is based on this work here by Morin, Siebert, and Weser in the deterministic setting, which we extended and complemented in order to make it work in the parametric setting here. So in particular, this tells us that the stopping criterion is always met. Okay, so in practical computation, so any tolerance at some points, you just have to wait and consume energy will be met. And a corollary of that, a straightforward corollary, is that under the saturation, so efficiently is always there, but reliability holds under the saturation assumption. But in particular, under that, the estimator and the energy error are equivalent, so we get convergence also trivially for the error in the energy norm. Okay, this is plane convergence, so this holds in 2D and in 3D, and so there are no assumptions basically. Now we'd like to start to move to convergence with rates. Okay, so and the first question is linear convergence, and the result is the following. You see it here. So we do get linear convergence. So in one iteration of the adaptive algorithm, our error is reduced. So strictly reduced. Okay, so there is a strict improvement, a uniform improvement, but the analysis requires some assumptions. In particular, yeah, so the saturation assumptions here plays a role, and our proof is currently restricted to 2D. And this is a fact associated with the use of the 2-level error estimators. Okay, but a comment that I would like, and so the proof is based essentially on this standard result. But a comment that I would like to make is the following: it holds a sort of there holds also a sort of converse implication, in the sense that if we have somehow an approximation and we get somehow, and we assume that we have a refinement of that multi-level structure, which needs to a greater space, a better space, and if the better space satisfy linear convergence, so if this estimate holds, then we can show that basically the way from moving from the previous the coarse approximation and the final one can be seen as the application of a Dörfler marking strategy with respect to certain marked multi-indices and elements, okay, which somehow justifies even more the idea of using combined Dörfler marking in our algorithm. And then, so the final thing that I would like to discuss for standard adaptivity is rate optimality. And okay, so we have seen yesterday more than one time how to rigorously define what rate optimality means. So we need a notion of approximability here, so which is basically apart from the translation that we have to do to match the parametric setting, it is the usual notion of approximation class of approximability. So in particular, this object here is finite if and only if the rate as is possible for our algorithm. And our proof for this estimator here, so for all the ingredients that I presented so far, we require a stronger saturation assumption, strong that in the sense that it implies the previous one, the classical one, let me call that in this way. And it is, so the assumption reads as follow. Essentially assume that, so there are two constants, smaller than one, having this form, such that the following holds. So if you have a mesh, an arbitrary mesh, and you get, if you have a multi-level structure and you have a finer one somehow, a multi-level refinement of it, and if it holds that somehow the error that you perform with the best one is better than the one of the previous one, then we require that somehow already one step of multi-level refinement from the start for the first one towards the finer one will already lead to a possibly small but uniform improvement. Okay, so this is the assumption. Okay, and we encountered that first while discussing the convergence of boundary element methods driven by two-level error estimators here. And the second ingredient that we need are somehow fine properties of multi-level structures and multi-level refinements, because, you know, so we also saw in some sense yesterday that we need some properties for the mesh, which are usually guaranteed by MVB, so-called overlay estimates and the so-called closure estimates. Okay, so here what we want to have is that the so-called coarsest common refinement exists, is unique, and satisfies this estimate. This is known to be true, say, when you talk about meshes generated by MVB, with our formalism somehow. So since we obtained that also for multi-level structure. So everything essentially boils down to the fact that this holds true for the meshes, okay, and the definition of our multi-level refinement and of the cardinality is such that also works also in this generalized setting. And the other guy is the closure estimate, which is this one here. So this is well known to all adaptive people here. And this also holds true in this setting here with in our context. And yeah, so this is the theorem, okay, the rate optimality that we have. So you see there are some assumptions, but basically, again, we have the standard requirement that theta is sufficiently small, so smaller than some threshold. This issue has been discussed yesterday in the talk by Christian Kreutzer. We have that as well, but under this assumption, we get rate optimality in this sense, okay? So somehow the sequence generated by our adaptive algorithm is optimal in this sense, okay? In the sense that if we replace the best theoretical possible guy, which appears in the definition of approximation class, by the guys generated by our adaptive algorithm, so this inequality holds true, okay? This is the result. Okay, to conclude the discussion about standard adaptivity, I would like to present again as a break. So I use numerical experiments somehow as a break between different theoretical results. This is a so-called cookie problem here, where somehow the radius of each cookie is fixed. We weight a little bit the importance by putting a different coefficient in front of them. And okay, what we see here again, here very briefly again, somehow the fact that the multi-level approximation delivers meshes that match the coefficients, basically the support of the coefficients. And here I made this test by considering different values of theta, so possibly larger than the threshold that we have in our analysis. And we see that, yeah, besides maybe the last one, which is a bit an outlier, okay, so 0.9, essentially but still the rate seems to be good also in that case. So essentially we get optimality, so the optimal rate, 1/2, again, so the best possible rate that you can get for each choice of theta. Okay, so now it's not clear to me how much time I still have, so. Fine. Okay, great. Then I can discuss goal-oriented adaptivity. And okay, so what is the question here? Basically, we have the same problem as before, and this is the solution of it. But what we want to do is not to approximate the solution itself, but a quantity of interest depending on it. Okay, and for simplicity in this talk, I will restrict myself to the case of a linear goal functional. So G is in the dual of V, but we can manage also some nonlinearities in our results. So with our results, and then the approach is I think. So we use the same that is used, for instance, in the deterministic setting. Okay, you introduce a dual problem here when the right-hand side is exactly the goal functional, and the left-hand side will be the same because here we are working with a symmetric problem. Okay, and then you consider just Galerkin approximations of both the so-called primal problem. So this, I will call that the primal problem, and the dual problem. And then what you get is this error estimate. So by construction, basically, you will get this error estimate for the goal, the error in the goal here, okay? So essentially, this can be bounded by the errors, so the energy errors for the U and for the Z, for the primal and the dual solution. That means that if you have at hand some estimators, okay, that are reliable, then basically you obtain a reliable error estimators for your goal error by computing the product of the two estimators, okay? And what you want to do is to somehow to design an adaptive algorithm which drives the product to 0 and possibly with the best possible rate, okay? So this is a bit maybe an extension of the previous question. And the adaptive algorithm will look basically the same, apart from the fact that in solve and in estimate, we have to do things 2 times, okay? We have to solve and estimate the error for both the primal and the dual problem. In mark, we have to do something. So we have one discretization, and we have to decide what we do, what to do, depending on the value of the error estimators. And here we follow this approach, which was considered by Rob and our co-author in this work, 13 years ago. And what we do is the following. So we do Dörfler marking for the primal problem and for the dual problem separately. And then essentially between the two, we pick the one with minimal cardinality, okay? And we use that in order to perform multi-level refinement. That means that in every step of the algorithm, I do either something, say, for the dual problem or either something for the primal problem. There are other choices are possible, choices that maybe from the empirical point of view seems to be slightly better, but not better in terms of rate, which is our focus. Therefore, I just go with this one, which is convenient for the theory. And so this is the algorithm. And again, a practical realization of it will stop when the product is smaller than some tolerance. And it's basically, we can extend the results that we had for standard adaptivity to goal-oriented adaptivity. So formally, you see it. So this is the convergence. So it looks the very same as before, apart from the extension. And also linear convergence and convergence with optimal algebraic rates formally looks the same, apart from the adaptation that you need for the different setting. Here you see the product of the energy errors are coming to play. And here you see that you have approximation classes for both the primal problem and the dual problem. And then you get optimality in this sense here with a rate which is S plus T, where S and T are those appearing in the approximation class of the primal and the dual problem. Some numerical experiment. Here I was really considering a toy, an academic example, somehow with a very trivial expansion, an infinite expansion, okay, of our, so we have an infinite number of parameters here, but my focus here was somehow to challenge a little bit the spatial resolution of the algorithm, in the sense that, so this is again in the spirit of this paper by Rob, somehow the right-hand side and the goal somehow enforce different part of interest in the domain, a square here and a triangle here. So the square is for the right-hand side and the triangle is for the goal. And then the support of the coefficients here is actually in this ball here. And then there is the corner singularity somehow. And what I wanted to show here with this picture is to show you that this approach somehow guarantees that everything is taken into account. So you see the support of the coefficient here resolved. This edge here of the square is also, so these 2 points here, as well as the 2 points here of the triangle, and finally, of course, the corner singularity. And you see some kind of grading in the sense which reflects somehow the strength of the singularities here. And here I have a look at the rates, and you see that for both the error estimate, so the estimator product, and the error computed with respect to a reference, a much finer reference solution, we get the optimal rate. So 1/2 plus 1/2 is 1, and this is what we get here. Okay, so this is basically what I wanted to say. So I come to the end. I presented an adaptive, so actually a framework to discuss convergence and rate optimality for multi-level stochastic Galerkin finite element method. So the method is, let me say that, simple in the sense that is based on what we know from the deterministic setting. So solve, estimate, mark, refine, combine Dörfler marking, and what we did was to somehow show convergence results. So plain convergence and restrict it to the linear convergence with algebraic rates. And we did this for this estimator here, so 2-level hierarchical error estimator. We have an extension of for goal-oriented adaptivity. I presented that for the linear case. We can manage also some kind of non-linear goal functional. Then, of course, the dual problem is different. It involves the Cateau derivative of the functional. You need some assumptions, but basically we can get comparable results. But what I wanted to say is that somehow we have provided a framework for the convergence analysis of this scheme, so the formalism with multi-level structure and so on. And if you would like to consider, for instance, other estimators, so for instance, residual-based error estimators, somehow you have to prove the properties on the estimator that you need, but then you can recycle most of the framework. This is what we are doing. A different question, which, as far as I understood, will be, for instance, the focus of the afternoon, so the talk in the afternoon, is I discussed optimality with respect to the number of degrees of freedom. Another interest, or possibly more interesting in application, is to discuss the computational cost. We need to work a little bit to obtain that with this approach, but this is in the long run, something in which we would be interested. And we hope somehow that our results can be helpful also to discuss convergence results also for other methods. So collocation and so on. We've seen that recently somehow stuff that we did for adaptive stochastic Galerkin FEM was useful to prove some convergence results for stochastic collocation. We hope that maybe also these studies can help somehow. So this is what I wanted to say. These are the references. Maybe I take 20 seconds for some advertisement here. So at Strathclyde, at the Department of Mathematics and Statistics, we have currently an opening for a lecturer position in scientific machine learning in a broad sense. So essentially anything apart. So you can go to PDEs, you can go to data science, but essentially it must be at least related in some form to scientific machine learning. The deadline is very tight, so it's essentially the 10th of April, but the application is not so heavy, I would say. So I would be very thankful if you have maybe good postdocs ready to jump to a permanent position that, yeah, to make some advertisement for that so that we get good people at Strathclyde. With this, I conclude my presentation and I thank you all for your attention.
Thank you.